Now let's put everything together and learn how to write the equation for any sinusoidal function. I'm going to overlook the equation up here and look at the graph first. So let's go back and look at how we are going to start analyzing the graph of a sinusoidal function. We want to look at 5 key points on the x-axis and 3 key points on the y-axis. So we're going to start with the high point. The highest this graph goes up is 1. The lowest this graph goes is -5. Halfway between those 2 points, which you can find by taking the difference from 1 to -5 is a difference of 6. Half of that is 3. So if I go down 3, I would get to -2. Or I could say 1 plus -5 is -4 and average that, divide that by 2, and I would get -2. So you find that halfway point, that middle point, that's the sinusoidal axis. So I'm going to dot that in, and I'm going to record those 2 values. And I'm going to use SA to abbreviate for sinusoidal axis now. So sinusoidal axis is y equals -2. Amplitude is 3. So we're going up and down 3 from the center, which is the sinusoidal axis. These are both changes in the y direction. Okay, so these are y changes. Then we're going to look at the x direction. And to look at the x direction, we have to decide whether we're doing sine or cosine. So we're going to start by doing a sine cycle. And when we do a sine cycle, we have to remember that a sine cycle starts and ends on the sinusoidal axis. Its midpoint is on the sinusoidal axis. And then it goes up and down in a pattern like this. So I have to cut out a section on my graph that looks like that. So I'm going to start on the sinusoidal axis and I'm going to end on the sinusoidal axis, and that is one cycle. So then I look now at my starting x value. So the x value that corresponds to my starting point is 3, and the x value that corresponds to my ending point is 23. I also have 3 other key points on my graph, and I want to also make a note of the x coordinates that correspond with those key points. So 8 corresponds with the high point, 13 with the middle point, and 18 with the low point. Now, we need to find 2 pieces of information about the graph in the x direction. Number 1, the period. The period, of course, is the distance from the starting point to the ending point of the cycle. And the starting point in the x direction is 3, and the ending is 23. So if we do 23 minus 3, that equals 20. That's the period of the function. So I'm going to write down here, period is equal to 20. The last thing is the phase displacement, or the start, which means the cycle starts. So we start at x equals 3. So there's my starting point right there. Now, when I want to write the equation now, I need to figure out places to put all those 4 pieces of information. So we're going to go up to the equation here, and let's remember what all of these different values tell us. We have 2 values that are outside of the function, denoted by a and c. One's multiplied times the function, one's added to the function. We have 2 values inside the function, b and d. One's multiplied times x, the other subtracted from x. So, by the way, this little arrow just was from a previous year when if you have the 2019-2020 notes, I left a parenthesis out, but you may be fine with your notes, so don't worry about that arrow. As a matter of fact, I may mark it off at this point, but I'll deal with that later. Okay, so anyway, recall that when we add outside the function, that shifts the graph up and down. It tells us the location of the sinusoidal axis. The graph has shifted down from its original sinusoidal axis of 0, so this is the sinusoidal axis. A tells us the amplitude, how much we stretch up and down from the sinusoidal axis. So this is amplitude, and that's kind of handy since it starts with an A. D is the phase displacement. Once again, displacement in D is kind of nice. So phase displacement, and that's, you know, our starting x value. I like to say that because phase displacement, I think, is not an obvious term. And then B tells us about the period. And so B is a value that is not the period, but it tells us how to find the period. So I am actually going to go back to what we've done the previous day with B, just to remind you of where B came from. So let's recall, we started with a graph that has a period of 2 pi, and my goal was to get rid of the fractions of pi on the x-axis and just turn them into regular integer numbers. So recalling from our previous values up here, when we multiplied by a number inside the function bigger than 1 times 2, it made the graph, the period, half as wide. And when we multiplied by 1/2, it made the period twice as wide. So we know that if we want to make the period go from 2 pi to just 1 unit, I would have to divide by 2 pi. To get 2 pi divided by 2 pi gives me 1, which means I'm going to have to multiply by 2 pi inside the function to have the same effect. So to get from cosine of x, which is this graph in radians, to the graph, the same cosine cycle but with only a period of 1, I have to multiply by 2 pi inside the function. Then, starting with graph number 2, which has a period of 1, I want to stretch that out, so now it has a period of 10, which means the period is 10 times bigger, which means I have to divide by 10 inside the function. So I end up with 2 pi over 10. Now, that leads us to the general idea that this value inside the function is 2 pi divided by whatever the period is. So let's go back to our notes now. That means in our notes here, let's write this. B is equal to 2 pi divided by the period. Now you might be wondering why I have this other equation over here. The only difference is that I took C from the end of the equation at the last piece and I moved it up front. I actually like this version of the equation better, and here's why. These two values, the C and the A, are both outside the function, which means they affect the y direction. These two numbers that are inside the function, the b and the d, these are, since they're inside the function, these two affect x. And we tend to look at them in pairs. We find the sinusoidal axis first, then we find the amplitude based on the sinusoidal axis. We find the starting point first, then we figure out the period after that. So we look at them kind of in this order, so I like to write the equation this way. So I'm going to be using this version of the equation. However, if you choose to add c at the end of the equation instead, it really makes no difference. So now that we have our four numbers and the form of the equation that we're going to use, then let's think about how to write a sine cycle. So I'm going to write f of x equals, so we start out with our sinusoidal axis, which is -2 plus the amplitude 3 times sine of, now the period is 20. So b is equal to 2 pi divided by 20, or pi divided by 10. Once again, it doesn't matter in the equation which way you write it, but later on when we solve equations, it's actually going to be very helpful and result in fewer careless mistakes if we write it as pi over 10. So I'm going to just write this as pi over 10. So if pi is in the numerator, that means the denominator is half of the period. Then our phase displacement, our starting point is a +3, so we subtract 3 inside the function. So this is the equation for this curve. Now I should say this is an equation for this curve, because I could have multiple equations for this curve because it is a continuous curve and I could pick different starting points. Let's say instead of a sine cycle, I want to write a cosine equation for the same curve. So what I have to do is identify a cosine cycle. And recall that a cosine cycle starts up high and ends up high, has its middle point, is its low point, and then it has two more points on the sinusoidal axis, concave down above the x-axis, concave up below, so it is curved, it's not a little V-shaped. So what changes here? If I look up here and I look for a cycle that starts high and ends high, I would be starting at 8 and I would be ending at 28. which means it still has a period of 20. From 8 to 28 is still 20. It still has the same amplitude, and it still has the same sinusoidal axis. The only difference is its starting point, and the fact that I write cosine in the equation instead of sine. So this is what the cosine equation would look like for the same curve. Negative 2 plus 3 cosine of pi over 10 times x minus 8 instead of 3. Now, when we talk about starting points, I do want you to kind of look. We could have multiple starting points here, but let's look at these key points. I want you to notice here, in a cycle, the key points are 5 units apart here. That's because the period is 20 and there are 5 key points, so in between each pair of key points is 1/4 of the period. So this is 5 units from here to here, this is 5 units from here to here, and so forth. That's one period. So this is 1/4 of 20. Now, of course, if I started at 8 and end at 28, then of course this is another 5 that would go from 8 to 28. That would be also another 5. So I'd like you to write down that's kind of an important piece of information. So number one, a couple things I want you to write down is the 5 key points, the 5 key points have x coordinates that are equally spaced. I'll just say spaced apart, equally spaced apart. Okay? So the 5 key points have x coordinates that are equally spaced apart. Number 2, this is a little bit unrelated to what we've been talking about, but I wanted to make sure to put this in here, is what's the difference between the period and the frequency of a sinusoidal function? So in this case, the period is 20 units per cycle. So one cycle is 20 units long. The frequency is the reciprocal of the period. So the frequency, we would say, is 1/20th of a cycle per unit. So every unit I do 1/20th of a cycle. Now frequency seems like a poor way to describe the length of the cycle of this graph, and it is in this case. 20 units per cycle makes a whole lot more sense than saying 1/20th of a cycle per unit. But what if the cycle was really, really short? What if it was 1/20th of a unit per cycle? It might be easier to say 20 cycles per unit. And so when we have very small periods, its frequency is often used as a way to describe how often the graph repeats itself rather than the period.